So real quick, let me get you started with your warm-up. So your warm-up, this is lesson 1 of the unit, Intro to Rational Functions. So for your warm-up, you don't need any pre-existing knowledge of anything, except for how to split up a pie. Okay? So we're going to look at a rational function in a funny circumstance, and then use that to help us start building understanding of what a rational function is. Then we'll dive into actual rational functions and graphing them. And this pie. So this is the way this works. There's a pie. It's being shared. There's just the one pie in every situation. Okay? Just a one pie. X is your number of people. Y is how much pie they get. So if there's one person and there's one pie, how much pie does that person get? One pie. But then his friend comes along, and he's like, all right, fine, we'll split it. So they each get half a pie, and so on and so forth. Okay? So that's how you get your Y values here. So that's how you get your Y values here. You fill those in. That's your X and Y. You're able to start plotting some points, and then just start noticing some things. Right? We're going to fill in the rest of the graph together, so you don't need to guess on what else happens. Answer these questions, right? Best of your knowledge, all the way through the line, and that's where you can stop, right? Don't move forward. There's some typos that, if you try to work forward, will mess you up that I need to explain when we get there, okay? So I'm going to give you some time to work on that. You're finding your X and your Y. You're plotting those points. You're going to have to do some estimating, because obviously if you have 1/2, well, there's no 1/2 line, right? So you have to do a little estimating, okay? I'll give you a little time. All right, so there's a pie. Like we said, if there's one person, he gets the whole pie, the whole one pie, right? But then his friend comes along and he's like, yo, can I get some of that pie? And he's like, all right, I'll be fair. I will give you 1/2, and I'll have a half. We both have a half. It's a very fair person. He's about to cut it up. A third person comes along, super fair guy. So he says, okay, everybody gets 1/3 of a pie. And so on and so forth. People just keep showing up. So 4 people get 1/4 of a pie. And then this guy, he's very lucky that he builds very big pies, because 25 people end up showing up, and so he cuts it into 1/25. Okay? But then he's like, man, people really like my pie. I'm going to do like a Guinness World Record, biggest pie you've ever seen. It's like the size of a driveway or something. And 1,000 people show up. How much do they get? 1/1000th of a pie. Okay, now we go to plot these points. We're just going to plot what we got so far. What was X again? What did it represent in terms of the situation? The number of people. And then Y was the amount of pie they got. Okay, so one person, X, got 1 pie, so X is 1, Y is 1. That's right there, okay? But then we say, okay, 2 people get half, so we go about halfway. 3 people get 1/3, so we go about 1/3 of the way. And your estimates start to get, just do your best zone, right? Because it's really hard to tell what a quarter is, right? Now, we don't have this on here, but what do you think 5 would be? 1/5, right? Right? 5 people, 1/5 of a pie. Now, 25 and 1,000, we can't plot those, but why do you think they're included? Yeah, because 1,000 is a huge number, but we still got some pie somehow, right? It's not all the way to 0. So it's just going to keep getting smaller and smaller and smaller. Which brings us to our point, our next question to ponder. How much, now this is kind of silly, but how much would each person get if there was 1 million people? 1/1,000,000th, which is a very small amount, and we got a little silly there, but it's making a point. Is there any amount we could go to, million, billion, zillion, where there would be no pi? No. There's no amount where it'll ever hit 0. We're always going to have a little bit of pi, the tiniest little fraction of a pi. Yes, we could go all the way to infinity and we still would not hit no pi. Okay? So we want to think about that and how that would show up on a graph, right? Now, next question, how is that shown on a graph? Like, what would happen as this continued to go?
It would get close to 0, but it would never touch.
Exact, or x-axis, right? So it would get closer and closer and closer and closer, but it would never cross it or touch it. Good. So it's almost like there's an imaginary line right here that it would just kind of approach but never touch, right? Okay, cool. Close to axis, never touch. And we're going to talk more about that phenomenon when we get down below and we stop talking about pies. Okay, now let's start to step outside reality so we can get some more points here. Now, before we talk about these, let's try to go this way. Let's go to 0. If there were 0 people, how much pi would they get?
0.
No.
Infinite.
No, nothing.
1 and 1.
No.
What did you say?
1.
It's 1 by 0 people. It's just the pi, not no 8.
Okay, answer this question without, just give me an answer. Ready? I have 1 pi. I want to divide it amongst 0 people. How much should each person get?
0.
Undefined.
Think about the question that I said.
Oh, wait. You can't.
I want to divide it among 0 people. How much should each person get?
You can't.
Your question, you should respond with what people?
Yeah.
There is no people. How could I even answer your question? That's a flawed question, right? If I can't answer the question, then, Hannah, it's undefined. It's literally a flawed question. I can't divide a pie among 0 people. There are no people, right? So you can't do that. Okay. So let's skip ahead to that final question above the line down there. It says, what would the equation of this situation be? Anybody know? We're going to talk about the other ones, but I'm just skipping for a second. What would the equation of this be? It's going to be y equals, and then every single time I took x, and where did it end up? Like 2, and then I had 1/2. 3, and then I had 1/3. 4, and then I had 1/4. It's 1 divided by x, right? I just take x, and I divide, and the first one, 1 divided by 1 is 1, so that stayed 1. But then I had 1 divided by 2, 1 divided by 3, 1 divided by 4, 1 divided by 1,000, right? So it should make sense that 0 was undefined. Can I divide by 0? No, our calculators don't like that, right? So we can't do this, right? So that's undefined, and that we're skipping all around here. So if x is 0, that's undefined, right? Okay, so where is x 0 on the graph? It's right here, right? But not just here, it's all the way up and down here, right? It's the y-axis. So we can't have an x of 0, right? So that's off limits, right? Okay, I'm just going to add another line there because it appears that that's another forbidden zone. Does that make sense? Yeah.
Would it be safe to assume that anytime we have these equations, they're only going to be located in one quadrant?
Not necessarily, but you're onto it. There is a break in them that happens where the quadrants happen. Okay. Now, let's talk about with x was 1/2. Well, now that we know the function is y equals 1 over x, we can start to look at a couple values that don't make sense for pi. Half a person, -1 people, that wouldn't make sense. But we can do it here, right? So if x equals 1/2, well, I would do y equals 1 divided by, and then what's my x? 1 over 2. So I have 1 divided by 1/2. Anybody remember how to divide fractions?
Multiply the opposite.
Yeah, you flip it. Keep, change, flip. You multiply by the reciprocal. So this is really like 1 times 2 over 1, which is 2. So if I'm thinking of this as a point, its x value is 1/2, and its y value is 2, right? So we can kind of add that to our table here. 1/2 is 2. 1/2 is 2,
That makes sense.
right? And then -1, well, that's y equals 1 divided by -1, which is -1. So the xy there is -1, -1. That's over here. Now, 2 became 1/2. 1/2 became 2. What's happening every time?
They're doing the opposite.
We're just flipping to the reciprocal, right? 1/2 to 2, 2 to 1/2. So what do you think 1/4 would be?
It would be 4.
4, right? Up here. And what do you think is going to happen along this one? The same thing. So, we're going to stop talking about pi in about 30 seconds. But this is what you end up getting. Okay? Now, on the negative side, the same thing will happen. But that didn't make sense for pi. We'll talk about that below. Okay? All right. So, this right here is your new parent function. Okay? So let's go down to the bottom. Your new parent function for rational functions. By the way, rational can be written as a ratio, meaning fractions. That's how this got its name, right? It's y equals 1 over x. Okay? Now, that word parent function is important. Remember how parent functions worked, right? This is a while back now. So remember, like, when you had, like, y equals x squared. Well, what happened is you got really good at that. You knew it started at 0, 0, went over 1 up 1, went over 2 up 4, right? And you memorized that thing. So that way, when I said, hey, what if I did x squared plus 3, you knew all you had to do was move this key point right here of 0, 0 up 3 spots, and then everything else moved 2, and you had your graph for x squared plus 3. Right? Sounding familiar? You memorized the parent, and then you moved it when you got changes. Same thing's going to happen here. So what do we need? We need a key point or 2. We need to learn this function so that we can move it. Okay? That's what today's lesson's about. So you're going to figure this out a little bit yourself. Now remember I said there was a typo here. When I made this table, I copied these values down and forgot to make them positive. So this should be all the same values but positive. We don't want to find them twice. So negatives to 0 and then positives. They're also in a little bit of a weird order, but you'll see why when you start plotting the points. It should make some sense. Okay? Now, to find these, again, you could remember that if it's y equals 1 divided by x, it's just a reciprocal situation. But if you forget that and you just want to do the plug in your x to find your y, well, this is what you would do in your calculator. You would go y equals, for this one, 1 divided by, and then what are we dividing by? The whole thing of -1 divided by 4 close. Okay? If you put that in your calculator, just like that, it will give you your y. or you can just remember how to do it. Does that make sense? So, well, I'll get you started here. What is 1 divided by negative 1/4? Negative 4. Okay, so you're going to fill in the rest of this. Now, when you're graphing these, it's a little weird because you're dealing in like fourths, right? So I made the graph to work with that. If you look at the graph, you can see that there are boxes in between the boxes for you here, right? So if this is negative 1, well, halfway there is negative 1/2 or negative 0.5. Halfway to that is your negative 1/4. So you would go halfway to halfway, and then go down to 4, plot your point, okay, and so on. Okay, so you're going to fill this in now yourself, paying attention to what's happening. When you finish, start thinking about these questions. We'll go over all this. I'll add some notes to help you remember certain things, key things, right? But this is what you're working on for now, okay? So you're filling in this table, plotting the points, graphing it kind of like we saw up above, and then we'll add some definitions and some key pieces, and then we're going to start practicing, okay? I'll give you some time to do that. If you're graphing negative 1/4, negative 4, just go over 1/4 of a 1 and down to 4 and do your best to estimate. It's not going to be perfect when you're estimating, that's okay. Negative 1/2 is at negative 2. Negative 1 is at negative 1. Negative 2 is at negative 1/2. Negative 4 is at negative 1/4. Okay? Same thing happens over here. At 1/1 we have a point. At 2 1/2. At 4 1/4. And then at 1/2 we're at 2. At 1/4 we're at 4. So it's just that reciprocal, right? What we end up getting is a graph that looks like this. Where we know it will get closer and closer to 0 in both of those situations, okay? So there's a couple different ways to talk about those situations. But before we do, I want to talk about those key points. Remember we talked about its parent function, right? So if we're going to move this thing around, we need key points that we can move, right? What are the only two good points that you see on this graph? 1, 1, and negative 1, right? So that point and that point, we can move pretty reliably. We know where they are, and if you tell me go right up 2, I just take that point and move it right up 2, right? We can move them. So we call these our key points. This is like the 0, 0 of your parabola. And it's half of what we need to graph. And when students have struggled with this graphing in the past, it's because they didn't start with the key points, right? They tried to move the whole thing, thought about the whole thing, just move the points first, and then things will start to reveal itself to you. But it's not the only thing I need, right? There's other pieces, right? So let's start talking about those pieces. What will x never be? Like, what is not possible? 0, right? Think about it. When x is 0, that's this spot right here, right? X is 0 the whole way, right? Is there any value there? No, it never touches it. Meaning, x will never be 0. X cannot equal 0. And that should make sense, because think about the function, 1 over x. If you plug in x, you have 1 divided by 0. That's not possible, okay? What value will y never be? 0, right? Because if we look at the graph, there are no points with a y value of 0, right? So y can never be 0. And that also makes sense when you think about the function, because there's nothing I can plug into this function that would get me 0, right? I could put in anything I want for x, but it won't be 0 as a result. Yeah?
What if you rotate the lines when they cross an axis?
Yeah, when we start moving things, there will be crossing. It's not always going to be axis. Okay. So that's why we need to figure out where they are now, because we got to move them too. So remember I said the key points is half of what you need? Those other things are the other half of what you need. So we got to start talking and defining those things. That's a good transition. What are these things? Like, how would you describe these highlighted areas? What do they look like? They're axes, but like you said, they might not end up just being right on the axes. What do we call things that are straight and go on forever? They're lines, right? They're lines. And how does the function behave compared to these lines? It doesn't touch it, right? Lines, the function doesn't touch. And we need a word for them. So, anybody have a guess what that word is? It's actually pronounced asymptote. It's a fun one, huh? Asymptote. So these are what's called asymptotes. The definition for asymptote is invisible line a function approaches but never touches or crosses for that matter. So this is, you're going to learn more about this in their next math class, but there's a limit to this function, and the limit is 0, right? It doesn't actually get to 0, but that's the limit. That's where it will stop. That's where your values will go until, right? That's what limits are, and limits are a whole subject in your next class. But this is essentially your first introduction to limits, right? Both with x and with y, there's a limit, and the limit is 0, okay? Now there's two asymptotes here. There's a horizontal one, and there's a vertical one. There's always going to be one of each, right? And we define them. We define them using our knowledge of how to write lines, right? Which one is our horizontal asymptote? Which color? The pink, right? Horizon goes across, just like the sun, right? So if you had to describe that line using an equation, you would say what? Y equals 0, right? Remember, lines going across, right? We're used to those. Those are our y equals. The weird ones are where it's straight vertical, right? That's kind of like outside of our y equals mx plus b situation, because they're not really functions, but we do have a way to write them. We say x equals 0. Okay, so in the parent function, you got asymptotes at x equals 0 and y equals 0, and you have these key points, right? And you need these to graph, because everything that moves the function moves all three of those things, okay? So we're going to practice that on the next page. The only other thing I'll add here is that a lot of times you'll just see the word HA, or the letters HA, or VA, so we don't have to write horizontal asymptote and vertical asymptote all the time, right? And this is why I asked you to grab highlighters. You will add these with highlighters, okay? To show that you know they're there, but they're not really part of the graph. You can use the same color. I used to, because you can grab another color if you want to. But it's really just if they're in a highlighter, you're good. Okay, so again, key points plus our asymptotes. So let's talk about how to use those, right? So you have this situation here. Well, we said the parent function is 1 over x. That's right here, right? And all they did was they added 2 to the outside of it, right? So based on our previous experience with parent functions, I'm like, all right, when you add on the outside, the function, if it, like say, was a parabola, it would go up, right? It would just go up 2. On the inside, moves it left and right, right? But this will make it go up 2, right? And any of these you can check on Desmos, right? Now, the horizontal asymptote, actually, before we get there, our key points, well, they were 1, 1, and -1, -1. Now, they're going to change, right? They're going to go up 2. So if normally I was at 1, 1, and I went up 2, I would end up where?
You would end up 2,
If I'm at 1, 1, and I go up 2, what's my new point?
3,
1, 3, right? And if I'm at -1, -1, and I go up 2, where am I at now?
1, 1.
-1, 1. Okay, so all I'm doing is moving those up 2. So my new key points are 1, 3, and -1, 1. So I add those to the graph, my new key points, right? Those are the key points moved up 2. Now, it's not the only thing that moves. Our horizontal asymptote, that was previously y equals 0, and it's going to become what? So if this whole line going across moves up 2, it will now be where? Y equals 2. And I add that with my highlighter. Okay. And my vertical asymptote was x equals 0. And if I move that up 2, does that change anything? No, it just takes an infinite line and budges it up 2. Like, that doesn't really change anything. So that's still x equals 0. So that stays. Now, hopefully you can see that if you add the asymptotes and you add the key points, the rest of the graph takes care of itself, right? Because the rest of the points were estimates anyway, right? So you just need to fill in this rest here and here, and that's your graph. What's that?
Is that the green pen?
It's a green pen, yeah. I could have used blue, but I wanted the key points to stay. Here, I'll use red. Here we go.
I just wanted to double check.
Now you got a Christmas theme here. Okay, so that's one movement of up 2, right? Now, this is where it gets a little confusing. We said our horizontal asymptote was y equals 2, right? We said our vertical asymptote was x equals 0. So our undefined values are what x cannot be, right? So if you think about it, if there's an asymptote at y equals 2, it's telling me, hey, at this imaginary line, you can't have a value. So y cannot equal 2, right? And then here, you can't have a value. So x cannot equal what? 0, right? So what's confusing is you end up writing y equals 2 and then y cannot equal 2 in the same problem. But these are saying different things. That's telling you a line, and this is telling you what y cannot be in our function, right? So that's a little confusing, but you'll get used to it. Okay? Now, this next one. Okay, I'm going to give you a little hint before you start on this one, right? What is 1 being divided by? X minus 3, the whole thing, right? So when we put this in, if we put this into a calculator, we'd probably put what around the x minus 3? Yes, because this is a group, and there are imaginary parentheses there. Now, why do you think it's important?
Because then you know that it's inside.
It's inside, right? That's now inside. So we're not talking about up and down. We're talking about left and right. Very good. Yeah?
Does the plus still make it negative?
Yes, it behaves the same way. Minus goes right, positive goes left. Okay? So go ahead and try that one. See how you do. Okay. So what was the prediction we came up with here? Because it's minus 3 on the inside, right 3. Okay? And our key points, right? 1, we'll do -1, -1, and 1, 1. Well, if they're going right 3, right, the x value is changing by plus what? 3. If you go right 3, you are adding 3 to your x value, right? So if I do that, I end up with, instead of -1, 2, -1, and instead of 1, 4. Add 3. moving right 3 to my x, right? Now, you can also look at the graph to do this, right? You could be like, I know I start here, so I'm going to go 1, 2, 3, and you get to 4, 1. I know I start here, so I'm going to go 1, 2, 3, right? So I have my 2 key points, okay? Now, the asymptote is typically, well, a horizontal is usually y equals 0. Now, we're moving right 3. Does that change this thing? No. You move an infinite line to the right 3, it's still an infinite line to the right. Okay? Now, our horizontal one, our vertical one on the other hand, x equals 0, well, that's this line. If I move that to the right 3, that sure is going to change things. What's that going to become? X equals 3, right? So this will stay, and this is x equals 3. And now I know I can just add my curves, right? And there's the function, okay? Now, what values cannot be defined here? Y cannot be 0, and x cannot be 3. Think about it. If x was 3, you'd have 3 minus 3 on the bottom here. That's 0. You'd be dividing by 0. It would break the function. Okay? That's why that happens. All right. Next one, last one we're going to be able to get to today. You have extra for practice if you want them. This one, by the way, you would do 2 movements. You'd go right and up, right? So a little more complicated if you want to try a more complicated one. But let's look at 6 because it introduces something new. Now, I remember when there was a negative out front with parent functions, what would that do, like to a parabola? It would flip it. So I'm just going to predict that, right? And we'll see what happens, okay? I guess I don't really even know what a flip looks like here, but we'll find out, okay? So we'll start with our key points. -1, and 1, 1. So remember when I had the x squared? What flipped? Was it the x or the y that flipped? Like if I had 0, 0, let's go to 2, 4. That became 2, -4. So what flipped there? The y just became a negative version of itself, right? So that's what flipping means? Okay. So then this becomes -1, 1, and this becomes 1, -1. Okay, let's add those points. So -1, 1, and 1, -1. Now, is there any movement right, left, whatever? Nope. So this is going to be just like our parent function. This will be y equals 0. This will be x equals 0. So I can just add those. And where do you think the rest of the points will be?
Going in the opposite direction.
Yeah, everything will be flipped, right? So this will end up being here, and this will end up being here. This will end up being here. This will end up being here. Notice that if you're picturing the parent function, all we did was flip it. You could even think about it as flipping left or flipping down. It's the same thing. Doesn't matter which way you flip it. Okay, now, undefined is just y cannot be 0, and x cannot be 0. And the only other thing is, just be careful, this is a flip and then a movement down, right? So don't think that that negative is distributing or something like that, right? These are 2 separate things, right? But you have every piece of the puzzle, so I'm going to hand out your homework.